Hello, welcome back to another session of Econometric Methods course. In the last class, we saw the properties and characteristics of OLS estimators. The other day we saw OLS estimators are linear, they are unbiased, and as the least variance in the class of linear unbiased estimators. That means OLS estimators are easy to compute and they are accurate and precise. And I assured you that in the coming classes, we'll see the practical application of these characteristics in the econometric practices. Today, in this session, we are going to see the practical application of those characteristics. Now let us consider a simple linear regression model. Y equal to alpha plus beta x plus u. To estimate the regression coefficients alpha beta, we derived using the OLS principles alpha hat and beta hat. Throughout our discussion, alpha hat and beta hat are the notations for OLS estimators. So in the classes previously, we saw beta hat is nothing but sigma xy by sigma x square, and alpha hat is equal to y bar minus beta hat x bar, where x bar and y bar are the means of y and x respectively. This formula is the most accurate formula to estimate beta and alpha respectively. We also saw the variance, the least variance of beta hat is obtained as sigma square divided by sigma x square. And also variance of alpha hat is equal to variance of beta hat into sigma x capital X square by n. For the large samples, it is also derived that beta hat follows a normal distribution with beta as the mean and sigma square by sigma x square as the variance. And therefore, z equal to beta hat minus beta divided by standard error of beta hat follows a standard normal distribution. And also, from the statistical theories, it is derived that beta hat minus beta divided by standard of beta hat for large samples follow t distribution with n minus 2 degrees of freedom. Alpha hat follows normal distribution with alpha as mean and sigma square by sigma x square into sigma capital X square by n. This is nothing but variance of alpha hat we saw previously. And also, for the large sample, z is equal to alpha hat minus alpha divided by standard of alpha hat follows a standard normal distribution, that is 0 mean and 1 variance. And also, alpha hat minus alpha divided by standard of alpha hat follows t distribution with n minus 2 degrees of freedom when the sample is small. In the practical application, variance of beta hat depends on the variance of random error. Similarly, the variance of alpha hat is also depends on the variance of the error term u. So, to apply these properties for the statistical inference, it is important to derive the unbiased estimator of sigma square. So, we are going to see how this estimator for this could be derived. So we are going to see the unbiased estimator of sigma square now. Now let us see how the unbiased estimator of the variance of the error term is derived. This is a very rigorous derivation. You must understand the variance is derived rigorously. Let us take the population regression function in the observation form. yi is equal to alpha plus beta xi plus ui. We also know that y bar is equal to alpha plus beta x bar plus u bar in the population regression function. Subtracting the above, we get the deviation form, that is yi is equal to beta small yi is equal to beta small xi plus ui minus u bar. Actually, we are getting this using subtracting these two equations. Consider the sample regression function SRF. Yi is equal to alpha hat plus beta hat xi plus ei. In a deviation form, we may write this equation as small yi is equal to beta hat xi plus ei. Comparing the PRF and SRF we are comparing these two equations. Yi, the term in the right hand side is made equal. So we get beta hat xi plus ei is equal to beta hat xi small xi plus ui minus u bar. Actually, this is the SR of yi and this is the PR of small yi. Now we are taking this term beta hat xi to the right hand side. So we can reduce this equation into beta minus beta hat small xi plus ui minus u bar. Squaring both sides, we are squaring this thing on both sides. We get ei square is equal to beta minus beta hat small xi plus ui minus u bar the whole square. We may use a plus b the whole square formula. We get a square plus b square plus 2ab. So the first term square beta minus beta hat xi square, that is beta minus beta hat square into xi square plus ui minus u bar square plus 2 into beta minus beta hat xi into ui minus u bar. So you get this expression. Taking summation, both sides we get sigma ei square equal to sigma, the same terms continue. So sigma xi square beta minus beta hat square plus sigma ui minus u bar square plus 2 into sigma beta minus beta hat small xi ui minus u bar. Taking expectations both sides, we get expectation of sigma ei square equal to expectation of small xi square beta minus beta hat square plus expectation of sigma ui minus u bar whole square plus 2 into expectation of sigma xi beta hat minus beta ui minus u bar. Here we have to be careful. Ei is the stochastic error, stochastic variable, and beta hat is a stochastic variable and ui is a stochastic variable. So this is what we have to keep in mind when you are dealing with the terms, because we have both sigma and expectation terms. We are going to take this into three terms: the first term, second term, and third term. We are individually handling each of the terms, and we are deriving the results. Let us take the first term, expectation of sigma xi square beta minus beta hat square. So that is equal to sigma xi square. The first term is taken. So expectation we are taking inside. So sigma xi square, the expectation of beta minus beta hat square. We all know actually this is the variance of the beta hat, that is equal to constant sigma square into sigma square divided by sigma xi square. So we are substituting this value for this. So we can cancel this, and we get sigma square. So the first term, see, expectation of sigma xi square beta minus beta hat square is equal to sigma square. Let us take the second term in the above equation, expectation of sigma ui minus u bar square. Now let us consider this one. We are expanding this term again, a minus b whole square. So a square plus b square minus 2ab. So that is the thing we are applying here. So sigma ui square plus sigma u bar square minus 2u bar sigma ui. So after expanding, you are taking the sigma inside. So we get three terms, sigma ui square plus, this is summing this n times, we get n u bar square. This you may take so this ui, sigma ui is nothing but n into u bar. Actually we know u bar is equal to sigma ui by n. So sigma ui is equal to n into u bar. So we get we substitute this value here. So now we may derive this equation further. We may reduce that. Expectation of sigma ui square plus n u bar square, and this we get 2n u bar square. Now we may reduce. Actually we may know this is n u bar square, and this is 2n u bar square, and by cancelling this we get minus n u bar square. So this is the expression we derive from this. Now we know that u bar square is nothing but u bar is nothing but sigma ui by n. So we substitute this value, and the same expression carried, and this term is expanded. U bar term is expanded square. Now we are going to apply the binomial expansion of this term. So the n is taken outside. This is n by n square, and this term, and we are expanding this term. We get binomial expansion. So ui square plus sigma ui square plus 2 into double sigma ui uj for I not equal to j. Right. Now you are taking the expectations inside. So if you take the expectation inside, we get sigma expectation of ui square minus 1 by n expectation of ui square minus 2 by n double sigma I not equal to j expectation of ui uj. Now we know the OLS assumption. The expectation of ui square is equal to sigma square for every I, and the expectation of ui uj is equal to 0 for every I not equal to j. So substituting this value, we get, instead of this, we get n times we are adding that sigma square. So n sigma square minus 1 by n into n sigma square again minus 2 by n into this term is 0. So this is 0. So this term will vanish, and at the end we get n sigma square minus sigma square, that is equal to n minus 1 sigma square. So this is the second term. So expectation of sigma ui minus u bar whole square is equal to n minus 1 sigma square. Take the third term in the above expression, the last term. So that is 2 into expectation of sigma xi b minus beta hat ui minus u bar. That is, we may arrange that, and we may take the expectations inside. So we get this term minus 2. Actually, this we are exchanging. This is beta minus beta hat, and we take the negative outside, so it becomes beta hat minus beta here. So minus 2 is minus is taken. So minus 2 is there outside, and beta hat minus beta is there, and sigma xi ui minus u bar. Now we have we may take this xi inside into the this bracket. So we get sigma xi ui minus u bar sigma xi. We already know this is this is the deviation values of x. If you sum that all across the sample, we get this value as 0. So we may substitute this value. If you substitute this value, this one term will vanish. So we continue the reduction, minus 2 into expectation of beta hat minus beta into sigma xi ui. Right? We already know this beta hat minus beta in our earlier session. We derived this is nothing but 1 by xi square into sigma xi capital ui. So we may substitute this value here. So if you substitute for this beta hat minus beta, we get 1 by sigma xi square into sigma xi capital ui into xi capital ui. So this is a constant term, so we may take this outside, and inside we have sigma xi ui the whole square, because now two terms are there. So we multiply, we get the square there outside. So now we do both. Actually, we are taking the constant outside and taking the expectation inside. So we get the expectation of sigma xi ui. Actually, this is again a binomial expansion we can make, and we are making an expansion of the summation, the square of the summation term. The square of the summation term, we get sigma square of this plus 2 into double sigma I not equal to j, the twice of this term. Actually, xi and xj terms will come. So we get xi xj ui uj. So this term is is the another term that comes with that expansion of summation square. So we get to know these two terms, and we are taking the expectation inside. We get sigma xi square into expectation of ui square plus 2 into summation double summation I not equal to j xi xj expectation of ui uj. So we already know this by OLS assumption. This is there is no autocorrelation, so we get this 0, and the terms are homogeneous, and so now the homoscedasticity assumption, we get sigma square. So this is what is the assumption is about. The expectation of ui square is equal to sigma square, a constant for all I, and the expectation of ui uj equal to 0 for all I not equal to j. So the second term will vanish, only the one term will remain. So we get minus 2 by sigma xi square into sigma square. So this is a constant, and we may cancel these two terms, xi square, sigma xi square terms. We get ultimately minus 2 sigma square. So this is the third term, the final value of the third term. We may substitute these three terms, and we get the expectation of sigma ei square is equal to sigma square, the first term, the value of the first term. This is the value of the second term, n minus 1 sigma square. This is the value of the third term, 2 minus 2 sigma square. Actually, we may take this sigma square inside, and we may break the bracket, and we get n sigma square minus sigma square. So this is now n sigma square minus sigma square and minus 2 sigma square is there. So the plus sigma square and minus sigma square will get cancelled. The remaining is n sigma square minus 2 sigma square. So we may take the sigma squares outside, and we may get n minus 2 sigma square. So now dividing both sides by n minus 2, we get the expectation of sigma ei square by n minus 2, and this is equal to sigma square. Right? This is by definition, this means sigma ei square by n minus 2 is the unbiased estimator of sigma square by definition. So sigma ei square by n minus 2 is the unbiased estimator of sigma square. Right? Let us give a notation for the unbiased estimator of sigma square as sigma hat square. So now sigma hat square is equal to expectation of sigma ei square by n minus 2. So I repeat, the unbiased estimator of sigma square is denoted as sigma hat square, that is equal to sigma ei square by n minus 2. Now we saw the unbiased estimator for the variance of the stochastic error term. This enabled us to find the unbiased estimator for the variance of alpha hat and variance of beta hat. Now with this, we'll use the estimator for the standard error variance to the estimation of the variance of alpha hat and beta hat, and this will help us to use these estimators for the practical application, namely the inferential statistics for the alpha hat and beta hat. In the next session, we are going to see the application of these results in the SLRM. Thank you.